hit record? You did? Just now? Just now? Okay, cool. I'll begin with a word of prayer. Heavenly Father, we thank you for this weekend just completed. Just pray be with us today. Help us to understand a little bit more about complex analysis. Pray you guide our thoughts and just help us to use this time wisely, Lord, to glorify you. In your name I pray, Lord Jesus. Amen. Okay, so let's see here. I had started to talk about forms, right? And so really differential forms. On the complex plane. And we had some language, right? We said that if omega, which was, let's say, p dx plus q dy, was equal to dh, where what was dh? Partial h partial x dx plus partial h partial y dy, right? Then omega is exact, right? Now, I have to be a little bit more precise about this. Domain matters here. If you talk about exactness without reference to the domain, it's not very useful. It's all about the domain here. So let's suppose that this is being true for some subset, D, some subset of C. So it's exact, to be more precise, on D, okay? So that identity has to hold for all points in D. And let's see, last time we proved some results about the integrals of differential forms, right? Around loops and paths. In particular, we established that, let's see here, what else, what proposition we established? One of the things we proved was if omega is exact on a domain D, a subset of the complexes, then the integral along gamma 1 of omega is equal to the integral along gamma 2 of omega for any pair of paths or curves, if you like, curves in D with same terminal points. Let's say matching terminal points. In other words, they begin and end at the same points, right? Now, what's the punchline here of this proposition I'm mentioning? That's so-called what? What does that say about omega? What's that criteria that I'm just describing here? Let me put it in a bubble. What's this define? Omega is path independent, right? On D. So exactness on D implies path independence on D, right? And it wasn't as easy, but we also, the next was one proposition we proved. Another proposition we proved was, path independent on a domain subset of the complexes implies, to be more specific, omega path independent also implies that omega is exact, right? I showed you that argument last time. We basically built the formula for H using an integration with a fixed point. Drew a little vertical line, horizontal line, argued that partial H, partial X had to be the X component of the omega, and so forth, right? Well, the content of that was omega was p dx plus q dy, right? And we constructed, what did we do over here? What was the proof, essentially? The proof was that we let H equal the integral from some fixed point, whatever, Z naught. Integral H of Z was the integral from Z naught to Z of omega. And we are able to show that this has, what does it have? It has partial H, partial X equals to P, and partial H, partial Y equals to Q. In other words, that is what? omega is equal to dh, right? So dh is said to be a potential for the form omega if that happens. That's what we went through last time. All right. I also shared with you guys the Green's theorem, and I reminded you the relation between integrals around a loop and path independence, but let's move along here. So the next definition we want to study, two really, is that of a closed form and then of what's known as a harmonic form. But first we'll start with closed. We say omega equal to, say, p dx plus q dy is closed on, let's say, d, some subset of the complexes, if what? The partial derivative of q with respect to x is equal to the partial derivative of p with respect to y on that domain D. So that makes omega a so-called closed differential form. So we can prove a proposition. I mean, essentially, that, what was that? I mean, why is that an interesting thing to define? I mean, there's various ways you could approach this, but I mean, in the moment of our current conversation, I would say this does what? This forces the integral blah blah dA term to be 0 in Green's theorem, right? Okay. Sorry, I'm still in reruns. Eventually I'll get to new material. So here's a proposition. Let's see here. How about this? If omega is exact, and I keep telling you, on D, right? On some domain of the complex numbers, then omega is closed. All right? How will we prove this?
Let omega be exact on D.
Very good. Michael's like, low-hanging fruit, I'm going to pick it. So he's like, let omega be exact on D. That's very good, though. I mean, honestly, if students could just do that, they'd get like at least 30% partial credit on most of my grading. Sometimes. Let's see here. Let's see here.
We have a class that teaches you how to prove. So then you can just.
Okay, so then what?
Supposed to prove it.
So yeah, right.
Partial credit.
So what's this mean? Omega is exact means that omega, which is equal to what? It's partial h partial x dx plus partial h partial y dy, right? There exists h from the d's to the from the domain in question to the complexes, such that omega is the total differential of h, right? So what's this make? Thus what? The p is what? It's partial h partial x, right? And q is partial h partial y in the language of the definition, right? So what do we need to check? We need to calculate partial x partial q, right? Partial xq is what? It's partial x of what? In this case, partial h partial y, right? Now, admittedly here, I need to borrow from the future a little bit here. There is a nuisance here. I need to know that h is twice differentiable and twice continuously differentiable in order to apply Clairaut's theorem. It's going to turn out, as we develop the theory further, that that's automatically true given the assumptions that we have here. But at the moment, I'm just going to have to tell you that there's a leap in our argument. So, jump. I'm going to assume h is twice continuously differentiable. It's not a bad assumption because in order to, well, anyway, I have to make that assumption here. So that means that this is partial partial y of partial h partial x, right? Again, that logical debt we will pay later in the course, okay? Just if I proved everything in order, then it would be less interesting. Sorry. Every once in a while I have to do this, and this is one of those places. Not my favorite course of logic, obviously, but anyway.
I think you're a lot more depressed about it than we are.
That's true. I am always more depressed about this issue than my students.
I mean,
but
I understand. I'm mildly depressed.
Oh, you're mildly depressed? I'll take it. I'll take it. It's a thing. Okay, so that's partial yp, and there you go. That proves it's closed.
It's not differential equations. So.
No, you can't make this kind of arbitrary distinction between courses. Differential equations are everywhere. Complex variables are everywhere. Linear algebra is everywhere.
No. I'm saying like it's less of a jump in logic than is often made in differential equations.
Oh. You mean differential equations is sloppier than this course?
Yeah,
Well, yes.
Yeah.
Of course, we're teaching it to engineers.
Mm-hmm.
For all in there exists, they're the same thing.
They get very mad when I suggest that we should have proofs in the class.
Yeah. Well, yeah, it's unfortunate. Okay, so there it is. Is the converse true? Let's look at an example, all right? So this is the standard example I give, and I'm always tempted to spice it up and give a different example. But what will happen if I try to do that is then I'll try to actually go to do an explicit integral, and then all we'll do for the rest of the day will be that integral, and then I will regret doing that. So I'm going to be boring and give you the standard example, which is this. Omega is equal to minus y dx plus x dy over x squared plus y squared, all right? So this is on the, there's one point where this is not defined, right? What? X and y equal to 0, right? So I'm defining this on the punctured plane, so C upper x, right? So C minus 0. Remove 0. Boop, boop. Okay. Is this a closed form? How would you check if it's closed? That begs the question. We don't know that. I proved the exact implies closed. We don't know about the other direction just yet. So is this, is this closed? So what's P? Minus y over x squared plus y squared, right? What's Q?
X over x squared plus y squared.
Right. Well, minus y. Oh, x, yes. I'm sorry. What have I done? Oh, I wrote it. I just don't believe it. I'm an idiot. Okay, sorry. I thought I wrote something different after you said that, but I've already written what you wrote. Written. Let me stop talking. Okay, so partial q partial x is what? You got what? You got x squared plus y squared minus x times 2x over x squared plus y squared squared. Right? Which gives me what? Looks like x squared minus y squared over x squared plus y squared squared. And what's partial p partial y? What did I do? Oh, yeah, sorry. So partial p partial y would be minus parentheses x squared plus y squared, close parentheses, minus y times 2y, all divided by x squared plus y squared squared. So what do we get? We get minus x squared plus y squared divided by x squared plus y squared squared. And you can see, woohoo, right. Yes, omega is a closed form. What is it?
Yeah, Sharon, what she said. There was a problem.
Boop.
Okay.
There's a minus in the original thing, and then there's another minus from the quotient rule. Well, anyway. Okay, so then what? All right, it's closed. Is it exact? Is this form exact on the complex plane? Well, remember, the other thing we proved last time was we had a theorem, right? Proposition, whatever you want to call it. If omega is exact, then the integral around a loop of omega is equal to a 0. Right? So this is a fun one. Integrate this thing around the unit circle. What happens? Continuing the example, what do we get? Consider the integral around the unit circle, right? So modulus of z equals to 1, and we'll counterclockwise that thing, omega. So that would be the integral from 0 to 2 pi. And I need a parameterization, right? So let's see here. How about x is equal to cosine t? Y is equal to sine t. So what's dx? What's dy? Sine t dt. dy is cosine t dt. And so you just plug those into omega, right? And what you get is, let's see here, minus y dx gives me a sine squared dt. And then x dy gives me cosine squared dt. So upstairs, I just get dt. And downstairs, I get what? X squared plus y squared, plug in x squared plus y squared, well, it's 1, right? I'm just plugging in these into the omega is equal to minus y dx plus x dy over x squared plus y squared, right? And if you look at the definitions I stated last class, that's essentially what they say, formally speaking. You can take differentials of the parameterization of the curve, plug them into the form, that's the integral. This corresponds geometrically to taking the dot product of the vector field with the velocity of the parameterization and then integrating over the appropriate parameter domain. And you can prove that this is independent of the choice of parameterization for the curve as long as it's oriented. But that's calculus 3. So here we get what? 2 pi. Ooh. Well, I don't know. I'm pretty sure 2 pi is not 0. So what's that say?
That it's not exact?
It's not exact. Now, not exact where?
On that circle.
Not exact on the circle. Now, we defined exactness for like sets, like open sets of, let's say,
So
for
on CX?
on CX, right? So this implies that omega is not exact. Now, I'm not sure it says that it's, well, yeah, I mean, for CX is one thing you could say. Certainly, if you take anything, here's the unit circle, right? You pick any domain, right, which includes the unit circle, you're in trouble. Right? Anything, if the domain you're looking at right? If that's the domain, all right, D, then omega is also not exact. on D.
So
If fitting.
you could choose a domain that does not include the unit circle, and then it might be exact if omega is closed.
Depends.
Right. That's what I'm saying. But theoretically, there might be some domain.
The possibility is logically open, yes. It could be that. But, I mean, it turns out if I look at, for example, this domain, we call that D1. Omega is also not exact on D1. However, if I was to, let's see here. Now it's hard to see curses. Let me make my D1 a different color. Where's my red? I don't know red today yet. Ah, here it is. So my silly black curve I'm just about to call D2. In fact, omega is exact on D2, but we don't quite know why yet, all right? So I'm telling you something we haven't quite earned the right to understand yet, but it would the omega would not be exact on D1. The critical thing is whether or not the curve encloses the so I'm saying take the curve and fill in inside the curve, right? If that curve encloses the origin, it's not going to be exact. Whereas if it doesn't include the origin, it'll be exact. I'm assuming that the loop's not self-intersecting. Simple closed curve, okay, yeah. So apparently, no. We cannot just, the converse of this is not true. Closed does not imply exact, at least in general. So is there some like extra hypothesis you can add to get a converse for this proposition? That's the question, right? That's where star-shaped comes into play, all right? So here's the theorem. If omega is closed on a star-shaped domain, then omega exact on that domain. All right, so how do you prove this? So let's see, star-shaped, let's just kind of draw ourselves a picture of let me make sure my star-shaped is actually star-shaped. There we go. What's the thing about a star-shaped region? Mm-hmm. So let's assume A is the what? The so-called star center of D. So for my picture, maybe I don't know, it could be something like this. And I want to prove that omega is exact on D, right? So I guess there's different ways you could attack this, right? You could try to prove that the integral around a loop in this thing was 0, right? You could try to prove path independence. You could just explicitly try to construct the potential function h, right? I mean, you got a lot of different choices for the method of proof here. I'll be boring and follow my notes. So the proof is just basically to make the right picture, and then once you have the right picture, everything kind of falls into place. Come on, where are you? So the picture basically involves drawing, so we're going to let h of z, so I'm actually going to construct the potential. H of z will be equal to the integral from the star center to z of p dx plus q dy. Now, I'm assuming that omega here is what? P dx plus q dy. Okay, that's given. Now, does that definition make sense? I mean, a to z is a line segment, right? So I'm pretty sure that a to z is the blue line in these arguments. Well, maybe not. All right, let me just draw the picture. We'll figure it out. So, let's see here. So I say fix a point z naught in D. So I'm going to fix a point z naught. That's probably my next step here. So there's a point z naught. Fix it. Then what? I say notice that the line segment from A to z naught is in D. How do I know that? How do I know that? Yeah, it's star-shaped, right? So that has to be in D. Furthermore, then what I do is I look at a little horizontal line to point 1 and a little vertical line to point 2. Let's see here. Try to keep with my color coding. So here's a little vertical line, a little horizontal line. Like this. All right. And then what I do is, so those are, the endpoints of these lines are what? Like this endpoint would be something like, so z naught is what? My usual notation for z naught is x naught plus I y naught, right? So what's the endpoint of the green line? It would be something like, the y naught's the same, right? But the x is variable, so it's x plus I y naught is the green line. And the green line has what? In terms of differentials, it has dy equal to 0, right? There's no y change in the green line. So when you parameterize that line, it has dy equal to 0. The vertical line, on the other hand, has an endpoint which would be something like x naught plus iy, and the red line has dx equals to 0, right? Okay, so then I can draw a blue. Oh, I was trying to draw a blue line, but I was tricked. As you can see, this is in fact not a blue marker. All right. So like this. That's supposed to be a line. All right. And now I've got a loop, right? Of a particular type. And let's see here. So I call the I think I call the little green line gamma 1, and I call the little red line gamma 2. All right. So gamma 1, gamma 2. This the black line is what? That's the line segment from A to z naught. And let's see here. What would the blue line be? It would be I'm going to bring it over here. What's that? It's I guess it depends on the orientation, right? If I go this way, then the blue line is what? It's the line segment from A to what point? X naught plus IY. Very good. Yeah. Okay. So we've got this is our setup. And what we're going to do is notice that this is, of course, a triangle, right? And I probably should, I should probably orient it in the positive sense. So the positive sense says you go around it counterclockwise, right? So the black line is fine. That's in the right direction. But my blue one, well, fine. If I go this way, right, then this should go that way, right? And that I should really go the opposite way. So if I think of these as the boundary for this triangle, all right? See that triangle there? What can I apply to a triangle? A triangle is a simply connected domain in the plane. I can use Green's theorem on that triangle, right? And so what we're going to do is apply, let me give that triangle a name. I think I call that triangle T, it's either T2 or T1. Yeah, T2. All right, so in my current notation, T2 has boundary. The boundary of T2 is, well, it's A to Z naught, right? Unioned with gamma 2, unioned with, well, the reversal of A to X naught plus IY, right? Now, what does Green's theorem say? It says what? It says the integral over the boundary of T2, right, of P dx plus Q dy is equal to the double integral over T2 of partial Q partial x minus partial P partial y dA, right? So what do we know about the term in the area integral? What do we assume about omega? Omega's what? It's closed, right? So by definition, this term is 0, which means that the sum of the line integrals which comprise the boundary have to be what? They have to be inverse. Yeah, sometimes. I don't know. So I almost feel like you can stop there in one sense, right? Because we proved last time if the integral around loops are 0, right, then that proves that it's exact. But then I guess it begs the question, can you make any loop out of triangles like this? So it's better just to go a little bit further and show that this actually does what you want. So, all right, so then what is this? We have integral from A to Z naught, right, of P dx plus Q dy plus the integral around gamma 2. Now, gamma 2 has what? dx equals to 0, right? So that just gives us what? Yeah, Q dy along gamma 2. And then minus, right? Minus the integral from what? From x naught plus iy to a of P dx plus Q dy equals to 0. Okay, so what's that really give us? This implies then that h of what? What's this? That's h of z naught, okay? What's this? That's actually h of x naught plus iy. Because when you flip the bounds, you get a minus because of the way line integrals work, right? But then so, oh, Curses. Sorry, all of a sudden I'm confused. So plus. Oh man, what did I don't want them to have the same sign. I've done something askew here. Oh, there's no I've invented an extra minus, right? I mean, what did I just do? I went from x naught to that point, right? So if I do it like this, there's a plus here, right? Because I'm going from here to there in my curve. In other words, I didn't actually do this. Instead, I did what? Yes, that's what I've just done. So there. Okay, so that's h of z naught minus h of x naught plus iy is equal to what? Integral minus the integral over gamma 2 of q dy. What is gamma 2, though? Mm-hmm. Right. So what's the parameterization of that curve? We just do what? We do x equals to x naught, right? And y is equal to t for what? What t was t range over? It ranges over y naught less than or equal to t less than or equal to y, right? So to be more precise, this is really, minus the integral from y naught to y of, let's see, what was q? Well, q is q. So q of x naught comma t dt. Man, I feel like I got another stupid minus where there's not supposed to be one. It's annoying. No, that's what I have in the notes. There may be a sign error here somehow, but so I argue then that if you look at the partial derivative of this expression with respect to y, oh, I'm sorry, I'm an idiot. Duh. So what happens if we differentiate? Look at this, I'm stupid. There's no sign error, it's fine. Look at this. Differentiate this with respect to y, what do you get? Differentiate with respect to y holding x fixed, what do you get? Does z naught have a y dependence? No, it's a fixed point, independent of the point y. So this gives you what? You get partial h, partial y at the point x naught plus iy. What's the derivative of this with respect to y? It's minus q of x naught comma y, right? And then as you let y go to y naught, you find at the point z naught, partial h, partial y is equal to q. Right? So this implies then that partial h, partial y at the point x naught plus iy is equal to q of x naught comma y. And then again, I gotta erase this stupid parameterization, it's in the way. Sorry. At that point, right? And then that implies, of course, that partial h, partial y at the point z naught is equal to q of z naught, which is half of what you need to show in order to prove that, in fact, h is a potential. This is that argument we went through last class again, but in a more specific context. Last time I was doing it inside a domain. This time I'm doing it inside a star-shaped thing, so we're using little triangles as opposed to the argument I ran last time, but it's essentially the same kind of argument. And then how would you get the partial h partial x is equal to p?
Could you differentiate with respect to x? That probably wouldn't work.
No, we won't be able to get it on here, but you just look at a different triangle. You look at the triangle that I'm just about to write, this one. See this one right here? You run the same argument over T1, and on that triangle, you'd discover about the partial derivative of h with respect to x. You'd be able to prove the other half of it there. All right, so I think I have hopefully spent enough time on that you guys can kind of see how the argument goes. Now, that doesn't yet explain my claim over there, right? How do you get from this to these claims, right? Well, there's another piece in the puzzle, the so-called deformation theorem. What's the deformation theorem say? Oh, I hope you got all that. You got all that? Okay. A little late to ask, but let me erase the evidence. Ooh. Oh. Oh. No. Unfortunate. I will leave the original. So there's another theorem. If omega is closed on D, which is contained between gamma 1 and gamma 2, then the integral along gamma 1 of omega is equal to the integral along gamma 2 of omega. Now, here I have in mind the following picture. See, gamma 1 and gamma 2 are two curves that have the same, I haven't written it yet, but I'm assuming that gamma 1 and gamma 2 have the same terminal points, all right? Otherwise, I don't know what this means, matching terminal points. Yeah, well, no. That was just a picture for that was a box for my picture, actually. That is not the domain. Thank you. Here, let me fix it. The domain I'm talking about is contained between them, so this is the D. What's the proof? Probably 3 or 4 different ways you can prove this at this point. Can you guys give me one? Mm-hmm.
I'm thinking.
Okay. Closed on D.
Yeah, let omega be closed on D.
Let omega be closed. All right, fine. Let omega equal to p dx plus q dy be closed on D. And I think that may be actually slightly insufficient. I think I am missing a little. I don't have an example to counteract this, but my spider sense is tingling. I do believe I need that. And omega is, let's say, nice. Let's say it's continuously differentiable on an open set containing D. So sometimes I would encapsulate that idea with just saying that omega is closed on D and is well behaved near the boundary of D. In other words, there's some open set like this on which omega behaves. Okay. Anyway. Okay, so anyways, the proof is pretty simple. It's just let d and the gamma 1 and gamma 2 be as pictured. Well then, d be the interior of gamma 1 unioned with minus gamma 2, right, which is a loop. So if you take two curves with the same matching endpoints, then they form a loop if you look at one followed by its reversal. And so I can apply Green's theorem on that set, right? So the integral around the boundary of d of p dx plus q dy is equal to the double integral over d of, partial q partial x minus partial p partial y dA. But again, that is by assumption 0, right? Because we're assuming omega is closed, which means the partial q partial x minus partial p partial y is 0, right? Which then says what? The integral along gamma 1 of omega is equal to the integral along gamma 2 of omega. Oh, and that's what I was trying to prove. Now you can up your game here. You can do it for regions with holes. If I have this is not just limited to a region. I can even do it for two loops, which, further application. I guess I'll put it over here. Continuing, another theorem. I just want to draw a picture here. If I've got this as, say, gamma in, and let's suppose that's oriented in the let's see here, clockwise sense. So orient gamma in the clockwise sense. And then I've got some other loop out here, gamma out, which is counterclockwise oriented. All right. And if I have a form, omega, which is closed between these curves. So suppose omega is closed on the deformed annulus, like all up in here. Oh, I'm going to regret drawing those hatchings. Let me get rid of them. So if omega is closed between the two curves, right? If it's closed all in here. Does that make? Do you guys know what I'm saying geometrically? Do I need to draw more pictures? Then what? Oh, sorry. I should have made gamma inward also clockwise oriented. Sorry. Idiot. Not you guys, me. Let's see here. So let's make them both counterclockwise. So they're kind of matching, right? Then you have the integral over omega of gamma in equals the integral over omega of gamma out. I lovingly refer to this theorem as the deformation theorem. There's one deformation theorem over here. This is another deformation theorem. Basically, if I can take, I have an integral. I can take the integral, the curve of the integration, and somehow continuously stretch it out to something else. And as I stretch the curve, right? As I stretch the curve, which I'll picture here with some intermediates. So you can think about, I can kind of continuously stretch the inner curve to the outer curve, right? And as I'm kind of expanding it out to the outer curve, as I go through that region, if the form is closed on that whole every intermediate curve, right? If that's the case, then I got this deformation theorem that says the integral of the inner is equal to the integral of the outer. How do you prove that, though? I'll make it look simpler. It's basically just this. You take the you take the region, you cut it in two, and then you have two simply connected pieces, right? And so on the top, you've got this way and that way from the outer curve, and the inside, I suppose you've got this way and that way. Now these ones, these cross cuts, they cancel because we're imagining them being like right on top of each other, right? And let's see, if I do these cross cuts the right way, I've got a counterclockwise oriented. So you just basically, the integral around each one of these loops has to be 0 because it's closed, right? So the integral around the loop is 0. And then if you study it, the cross cuts cancel, and you end up being able to show that this is equal to that. It's the same as the argument that was given in Calc 3. I can be more careful. Let's call this top one gamma top, gamma bottom, gamma. I need some names. Name names. N. That's bad. I tell you, I'll take n minus, and the top will be n plus, and actually let the top one be gamma out plus. This is gamma out minus with the obvious meanings. So if I call this region R minus and call this one R plus, then basically you have the integral over R plus, or well, let's say R plus, I'll just do the of blah dA. This blah is 0 because it's closed, and that has to be the integral. So what, R minus, R plus is what? You've got, let me call this gamma S and gamma SS, I don't know. So we have integral over gamma S, gamma S omega plus the integral. I need to have these counterclockwise oriented, right? So you see I get gamma S omega, then I get gamma out plus omega plus the integral over gamma SS omega minus the integral over gamma n. Why is it minus there? Because I have to I have to orient positively the region, right? So that to go the opposite way to get a counterclockwise boundary. You do the same thing on the lower region, and then you add the two Green's theorems together. When you add them, the cross term, the gamma SS, and the one right below it cancels. This one cancels, and you're left with gamma out plus gamma out minus gamma in minus gamma in minus, and so you get that the sum of the in and the out integrals are equal and opposite, and that's the deformation theorem. And that's how I knew over here that I could, if I don't encircle the origin, I know I'm not going to get into trouble. If I do encircle the origin, there's no way I can deform past the origin. The origin's the problem point. That's where, oh man, I erased the x squared. That's where this is 0, and that's where the problem is. Anyway, we'll talk more about this Wednesday. So thanks, guys.